All right, in this video we look at, again, section 15.5, but we'll try to focus on um, the interpretation of this triple integral. Okay. So what we're seeing here is a triple integral that has been given. Okay. The ordering for dv that has been chosen is dz, dy, dx, which means that our domain D, we can figure that out from the limits of integration here, that D is a cube where Z, it's a Z by Y by X cube. Z goes from 0 to 1, Y goes from 0 to 1, X goes from 0 to 1. And that's what we were seeing in this picture, that X goes from 0 to 1, Y is going from 0 to 1, and Z is going from 0 to 1. So we have this cube here, okay? And we are, sorry, let me finish this picture. So we have this cube. I don't know why I'm spending so much time on that. There we go, we have a cube. And we now have a function, of 3 variables, which is x squared plus y squared plus z squared. Now we know that a function of 3 variables, that this is somehow 4-dimensional, right? But we can think of that 4-dimensional object as 3-dimensional. Think of this as 3-dimensional level surfaces. So what we can think of is setting the value of the function maybe to be equal to 1. And when you look at the function values equal to 1, we'll have x squared plus y squared is equal to z squared is equal to 1. All right, so 1, according to this plot, is a blue. Right, so what we're seeing here is that all the points that are at a temperature of 1 are on a sphere of radius 1. So what we're seeing here is that this plot, this level surface, is a sphere of radius 1. Okay? If we move to different values of the function, maybe function equal to 3, then we would see x squared plus y squared plus z squared is equal to 3, and we would see a sphere of larger radius. Okay? And what we would be seeing would be that this cubical region here, right, it has to be, it's not just a region of, it's a region of space, but you need to imagine that it's filled with some sort of material. Okay, and that material is given by what the function is. So when the function value is 1, we can see that this material is has the same density, right? The 1 is the density, for example, and all the points on that sphere of radius 1 are all at the same density. And then when you move to different points, choose a different value, that we will also see a sphere, right, that is at a different density. Okay? And different points in space are at different densities, and this space is filled, according to this density function, filled with spheres, right, that are of different radii, and all the points on those spheres are at the same density. Okay, so that is what this function is telling us. And according to what we have talked about in a previous video, we are doing a triple integral of this function, this density function, over a region of space, D, which is this cube. And by doing this triple integral, we are going to get the mass of this region D, where the material that makes up this region varies from point to point. It's varying densities. Okay, so that is the setup of this, an interpretation of this triple integral. The rest is just to evaluate it. Okay, we can go ahead and walk through the evaluation step now on the next page. So we're integrating over a cube, 0 to 1, 0 to 1, and we're integrating the function x squared plus y squared plus z squared. And we were integrating in the order dz, dx, let me go back, dz, dy, dx. dz, dy, dx, and z went from 0 to 1, y went from 0 to 1, and x goes from 0 to 1. Alright, so tackle the first integral first, and that will give us, once we're done, the volume of the region D. So integrating with respect to z, you'll get x squared z plus y squared z plus z cubed over 3. And we want to evaluate from z going from 0 to 1. That is this first integral. So we'll get x squared plus y squared plus a third. Okay. And now we move on to the next integral, y is equal to 0 to y is equal to 1 of x squared plus y squared plus a third, integrating with respect to y. So that would be x squared y plus y cubed over 3 plus a third y, evaluating from 0 to 1. So that would be x squared plus a third plus a third. And because the bottom limit is y equals 0 and all these terms have y, that will go away. The y terms will go away. And finally, we're at the last step, integrating from x is equal to 0 to x is equal to 1 of x squared plus 2/3, integrating with respect to x, we'll get x cubed over 3 plus 2/3 x, evaluating from 0 to 1, 1/3 plus 2/3, and the answer should come out to be equal to 1. Okay, so that is, I'm sorry, not a volume integral, this is a mass integral. So the mass of that region, okay, this is the mass of the region D. If we had just been integrating with respect to 1, integrating the function 1, we would have just gotten the volume of the region, which would have been a 1 by 1 by 1 cube, which would have been a volume of 1, I guess. Right? But now that we have well, it would have been 1 unit cubed, of course. But now that we've got a density function, okay, now that we have this density function, we're seeing that because of the uniformity and the density, that we're getting a way to interpret this as 1 kilogram of mass. Okay, so there is one problem where we get to interpret as mass. We've evaluated the integral. The integral was already set up for us, and so there's no real difficulty with the setup phase of the integration. Okay. Problems get more interesting when there is less information given. Okay, so this problem says to write the 6 different triple integrals for the volume of the tetrahedron that's been cut from the first octant by this particular plane. So there is seemingly not a lot to go on here. It seems a little bit short on the information. And then it says to evaluate one of these 6 possible integrals. Okay, so here we can see that we need to do all of the different steps. We need to do a sketch of this region. we need to do the setup of the integral, and then we also need to do the evaluation. Okay, let me unlock my machine here. It went to sleep on me. Okay, so let's get a sketch of this region. Okay, we can see that the surface given is a plane, right? And this plane needs to come through into the first octant. So here's the x-axis. We have all these different coordinate planes, as we've looked at in previous problems. So we have this plane, and this plane. The x, the y, and the z equal 0 planes. And then we have the plane given in blue coming in. And that plane is going to intersect each of these other planes, okay, and create this triangular region. Okay, this takes some practice to see. And what we've been asked to do is to find the volume of the region that's in here, inside of this triangular region. Okay, to get a better picture of this, if you would like to see it, we can just do a contour plot 3D. We can look at all of the coordinate planes. X is equal to 0. Sorry, let me make this font a little bit bigger for you. X is equal to 0, y is equal to 0, z is equal to 0. And then there is another plane, 6 times x plus 3 times y plus 2 times z equal to 6. And we're not sure quite where to plot that from. Let's go, but it's in the first octant, so x has to be bigger than 0. Y has to be bigger than 0. And z has to be bigger than 0. And now we need to fill in, let's just take a guess that maybe x goes from 0 to 4, y from 0 to 4, z goes from 0 to 4. And then we can refine this picture as needed. Okay, and we'll do some algebra to solve this out. So there are the two different planes, 3 different planes, the coordinate planes, and we can't really see the volume because these plots are not opaque. So let's do contour style. Let's make these see-throughable. And we can see this region that we're looking for the volume of. We're looking for the volume of this tetrahedron. So there's this plane coming in, and the part in orange, this triangular region, and the part inside, that is the tetrahedron. So it's a triangular region with some flat walls. Okay, so we've kind of got the sketch part done. Okay, if we want to do the setup, you need to decide on what ordering for dV you want to use. Okay, one obvious choice is we're used to probably thinking top, bottom, then, oh, sorry, Jason, that Z is an X. We're used to thinking top to bottom, up and down. We're then used to most likely dealing with the Y variable first and then X. So this is a common ordering that people feel most comfortable with first. Okay, so let's decide what we need to do. We're trying to find a volume integral. I said to find the volume. I think so, for the volume, correct. And we're going to do a triple integral to compute volume, so our function f needs to be equal to 1. We're going to do the z variable first, which means we need to go from the z equals 0 plane up to the given plane. And the given plane is right here, and we'll need to solve that for z. So z would be 6 minus 6x minus 3y, and then divide by 2. That is the z. 6 minus 6x minus 3y divided by 2. And now we're done with the three-dimensional aspects. We are now into the xy plane. Okay? And now we need to finish the other two limits of integration, the x and the y's. Okay. But this plane comes through and crosses into the xy plane when z is equal to 0. When z is equal to 0, we get 6x plus 3y is equal to 6. And then if we want to do the dy integral next, we need to solve for y. Okay, and we could see that that line 2 minus 2x has a y-intercept of 2 and a negative 2 slope. So this region that we're seeing here in the xy plane is this region right here. And then y would go from 0 up to whatever this line was. Y would go from 0 up to that line, which is 2 minus 2x. And then we can see that we need to then finish the x integral last. Okay, and the limits are x going from, we need to figure out when y is equal to 0. So y is equal to 0 when x is equal to 1. So we have x going from 0 to x is equal to 1. And there is one possible ordering, the dz, dy, dx ordering for the volume of that tetrahedron. Okay, the rest, I will leave the other 5 integrals for you to set up, and you'll know that you will have set them up correctly if you evaluate your integral and it comes out to be equal to, let's figure out what this integral evaluates to. Okay. We're going to be integrating the function 1. We try to do the dz, dy, dx. X goes from 0 to 1. Y goes from 0 up to 2 minus 2 times x. 2 minus 2 times x. And z goes from 0 up to the equation of the plane, which is 6 minus 6 times x minus 3 times y divided by 2. So when you evaluate that volume, you will get, oh, you see that I should have gotten a number. That means I've done something wrong here. And something wrong I did was I mistyped the plane, so that should be minus 3 times y. So you get 1 again as our answer. It's a bit anticlimactic. Okay. Something else I want to do to verify that this number 1 is correct, I like to check that our 3D limits of integration, the dz, the dy, and the dx, make sure that those are the right limits of integration. And the way to do that is, as we've done in the past, do a region plot, 3D. And we can see that z is, according to our limits of integration, z is supposed to be bigger than 0, but less than the plane, 6 minus 6 times x minus 3 times y divided by 2. And y is supposed to be bigger than 0, right here, but y is supposed to be less than 2 minus 2 times x, and x was supposed to be bigger than 0, but also less than 1. So if we get a region that fits right into where that triangle is, where the tetrahedron is, we'll know that we have the right answer. And so let's show these two plots together. Okay. And it's a bit lumpy, and it doesn't quite fit like you would expect. But that is just the nature of the computer. If you plot points, if you make the computer plot more points, like 30 of them, you will see that it'll start to fill out. Let's go to 50. That it should fill out the region that we're looking for. Okay? So that tells me all 6 of the limits of integration I've done are correct, and the computer checks that that volume is equal to 1. And so when you try, for example, some of the other orderings, like the dy, dz, dx, or the dx, dy, dz, right? You should also get 1 for your integral. I will leave that to you.